Hi, welcome. So now we will quickly see the non-hierarchical clustering, and what we are going to see is the k-means clustering technique. K-means is one of the most used non-hierarchical clustering, and as I already mentioned, when you have large data sets, it's preferably to go with the k-means clustering. Uh, it makes use of within cluster variation as a way to find out which data to merge. Okay, and the entire algorithm is objective is to segment data such that within cluster variation is minimized. Okay, the flow of algorithm, how it works, what we have to give to this algorithm as a starting point is how many clusters have to be formed. If you see in a hierarchical clustering, we started off with the data and algorithm executed, we got a dendrogram. After having looked at a dendrogram, we had to say how many, where the cuts should be there. We had a visual output and then said that okay, 3 clusters, 4 clusters based on the visual output. Here upfront we have to say how many clusters have to be formed, and then the entire algorithm, which is steps in English, is given here. Okay, dot is given in English. Let me try to explain through a slide. Let me insert a blank slide. Let's try to understand. Assume these are the two dimensions, x1 and x2. You can consider these two dimensions as same as brand consciousness and price consciousness. All right. And on these two dimensions, these are your various data points which are spread. Let me change the color. And now we provide that this data we have to cluster. And as I said, the input, how many clusters to be formed has to be given upfront. Say the input that we want to form 3 clusters is given as an input. So randomly 3 centroids, 3 cluster centroids will be randomly considered with x1, x2, whatever is the parameters. So that centroid, say C1 is coming here, C2 is coming here, and C3 is coming here. Now with respect to C1, what will happen is distance of all these dots will be computed. For all the dots, the distances would be computed. All. I've just shown some indicator. Similarly, for C2, the distance of all of them will be computed. And so forth. Similarly, for C3, all these dots will be computed. Now, whichever point is closer to whichever centroid, that point will go in that cluster. Whichever point is closer to whichever centroid, that point will go into that cluster. So assume this part of the points are closest to C1, so they will go in C1. This set of points are closer to C2, as such they will go in the C2, and the remaining, they are closer to C3, as such they will go in C3. Yeah. The moment these points have become part of cluster C1, can I recompute the centroid of these set of points? I can. So I'll take average of all attributes and I'll get the centroid. So if I take x1 attribute for all of them and average, then probably that x1 may come somewhere here only. And when I take x2 attribute and average of all of them, then it may come somewhere here. So this becomes your new centroid C1. Likewise for this centroid may come somewhere here. And this probably may move somewhere here. I don't know. Okay. Once the new centroids are done, old centroids make no sense. So this centroid will go off and this new centroid is there. So all these centroids will go off. Okay. So these are my new centroids. Again, the distance will be computed. And now when new distances are computed, certain dots which were earlier not closer to C1 may become closer to C1, and certain dots which were earlier closer to C1 may become farther to C1 and may probably become closer to C2 or C3. The moment certain dots, certain records which were closer to C1 and now become farther and they have become closer to C2, they will move into C2 centroid. Those which were closer to C2 but now are not closer to C2 but closer to C1 or C3, they will move into the respective centroid. As such, those records will move from one cluster to another. Again, iteration will happen. New centroid average, again iteration happening. New centroid average, again, and this process keeps happening. This process keeps happening till no record moves from one cluster to another. However, to reach that stage when no record moves from one cluster to another, if you have a very large data set, may take maybe too time consuming, and it may also happen that at times it may reach into a stage where one record moves in one iteration in cluster C1 and in another iteration it jumps back in C2. Because as one moves here, the average will change. And because of that, continuously they may keep jumping and we may not have ultimate convergence. So what we have to do is we have to say after these many iterations, whatever is the status is the convergence status. Make sense? And that is the algorithm of k-means clustering. That's the algorithm of k-means clustering. And here the advantage is you have only, say now because you have taken only 3 dots, the combination of those 3 dots with respect to all the points distance has to be computed, and not all dots with respect to each other distance has to be computed. So the amount of computation is reduced drastically. Amount of computation is reduced drastically. And that's why k-means clustering is a faster algorithm than the other technique. Yeah. And this is entire English verbose thing. Assume k centroids. Compute Euclidean distance of each object with respect to the centroid. Assign the objects to a cluster with the shortest distance. Compute new centroid of each cluster based on the object assigned to each. The k number of means obtained which become the new centroids for each cluster. Repeat step 2 to fro till there is no convergence. Till there is convergence. That is, there is no movement of object from one cluster to another, or threshold number of iterations have occurred. That's what I explained. Advantage, it's a superior technique compared to hierarchical, computationally very fast, and preferable to use on interval or ratio scale data. as it uses Euclidean distance. Desirable to avoid using ordinal data, where ordinal data, ratings, feedbacks, those kind of data set, where all data is in rating format, 1, 2, 3, 4, 5. In that case, Chebyshev distance has to be used, but K means makes use of Euclidean distance in the algorithm. Okay. Only challenge is number of clusters are to be predefined. That is actually not a challenge, because there are ways to find out optimal number of clusters before you run the k-means clustering itself. Now, before I go into the code, why optimal number of clusters finding is important? Just a graphical representation of data, D1 and D2. If I say that I want to form two clusters, what will happen is I can get this as a one potential solution, and this is another potential solution in a two cluster format. If I say three clusters with this kind of data, probably this would be a one solution, this second solution, third solution, and fourth solution. Now when you run the clustering algorithm, what may happen is, if you pass suboptimal number of clusters, it may so happen in one iteration it will give this output. Say I pass 2, so in one iteration it may give this output, in another iteration it may give this output, which is not stable. If I pass 3, it may give one of these 4 combinations which are shown at bottom. Best solution in this kind of data is 4 clusters. Anytime you run, it will give the same, right? So that's where the clustering algorithm finding optimal is important. Yeah. So let's see how do we go about doing the k-means clustering. First step, I'll import the data. Okay, I'm going to this is the same data set on which we are running the k-means clustering. We are scaling it. Okay, so view scaled, class it. Now how to find out optimal? So there is a piece of code which I got from net, which says the entire objective is, as you merge clusters, what should happen is within sum of squared of the cluster should be lower. So basically, if I see the entire data at a whole, my variance will be high. Now, the moment I split it into two, the variance of this component, one of the cluster and the other, would be lower than the overall variance. And relatively, there will be a reduction in variance within sum of squared error. So if I do 3, there will be further reduction in variance. So the point till which I get good amount of reduction. So if I say I start with a data set having 100 observations, and then I split and I get 2 clusters, there will be a certain level of cluster variance within sum of square error reduction. If I make 3, there will be further reduction. If I make 4, it will be further reduction. Okay. The point where the reduction plateaus, obviously, if I make 100 data points are there and make 100 clusters, definitely within WSS will be 0. But the objective is not reach 0. The object, if that was the objective, then why do clustering? The objective is to find with minimum number of clusters how maximum amount of within sum of squared can be reduced. So there is a this function which I'm just going to run. What it does is it does various combinations. It says that, okay, if I find one cluster, if I would do one cluster, what is my WSS? If I would have made 2 clusters, there is a reduction. This much is a drop. If I do 3, there is a sharp drop further. If I do 4, there is a plateauing now. So this type of plot is called a Scree plot, and where the elbow formation, basically this elbow formation happens. So this here, the elbow formation is somewhere here. So where the elbow formation is there, that point is the optimal number of clusters. So from this, 3 number of clusters for my data set is optimal. Yeah. If we don't believe in that, then there is a package called NBClust. In that package, there are many tests it does. And after that many tests, it gives you the optimal number of clusters. So here if you see the documentation, NBClust package provides 30 indices for determining the number of clusters and proposes to user the best clustering scheme from the different results obtained by varying all combination of number of clusters, distance measures, and clustering methods. So it does various tests in the background. So here what I'm just running on the same data, some set of code, and then saying what is the optimal number of clusters. So here it says 0, 1, 2, 3. Of the many tests that are happening, 18 tests, or there are 18, 5, 23 plus 1, 24 plus 2, 26. There are 26 tests have happened. Of the many tests, 18 tests are saying 3 cluster is the optimal number of clusters. I can just show the same thing in a bar plot. Many of them are showing that this is the optimal. Okay, so it's some NBClust package which we just read the documentation. What are the various tests? I just show that once again. What are the various tests? Distance, sorry, not this one. So here see, these are all tests. KL, CH, maximum value, this, CCC, Scott. By the way, SAS makes use of CCC. Okay. So these are various tests. What are the definition? What are the interpretation? Frankly speaking, I don't know. But okay, there's a package which does all of this, and based on that, it gives you output. Why not use it? So directly using that and to find my optimal number of clusters. Once you have done that, then once you know that these are the optimal number of clusters, there is not much of a problem. Why? Because you have to directly pass that as input and run the code. So here I'll have to use a scale data set. For clustering, you always use a scale data set. Centers equal to 3. I'm now saying 3 clusters to be formed. N start equal to 25. So basically I'm saying that when you're doing clustering, start with 25 different combinations of random starting points. What may happen is, for example, a theoretical one. Okay, that data is resume slideshow. Yeah, there's a theoretical thing, but quite possibly that when I start with the random, C1, C2, C3 all come here, and then probably in the given number of iterations, things may not converge, right? So I'm saying that n start equal to 25. So there will be 25 different times it will create different random numbers and do the clustering. So that's what the documentation says. Let's see the documentation aspect. N start. How many random sets should be chosen? Yeah. So this is a simple formula. We run, my clustering is done. My clustering is here. So it shows you what are the cluster means. Now this means is not going to make much sense. Why? Why is it not going to make much sense? Because these are on the standardized variables. So we cannot interpret it. This shows what are the within sum of square for each of the clusters. So between SSS divided by total SSS. So there is a 60 percentage. So between sum of squared as a percentage of the total sum of squared is now 60 percentage. There is a reduction of 40 percentage. Yeah. So sorry, between SSS there is a reduction of 60 percentage, and these are the various components, various other attributes which we should not much bother about it. But once you have that, What is main objective? Once you again do the clustering, what is the next steps? See the profile. So what I have want to do is, these are some temporary code which I have inserted. I don't want those codes. Bar plot, this is the output. If I want some graphical plots, these statements, libraries and all those things, I'm not going to go much into details of these graphical plots. But yeah, if you want the graphical plots, what you can simply run is that I leave it for your own self-interpretation. This one, it shows you graphically where are these. What happens is when the clustering are done, internally important dimensions are created. So there's a one dimension, two dimension, or two important dimensions. On those two important dimensions which are considered, all the dots are plotted. Okay, but these things will not help us much. If you want some more graphical things, basically I want which of the dots are close to each other. So there is a component 1 and there is a component 2. These two components explain 66%, 67% of the total variability in that data. How are these components formed? Let's not go into that details. But more important is which dots are closer to each other. Graphically, it says that 3, 4, no. Why is this 3 again? Sorry, this number is 1. This 3 is basically the cluster number. 1, 4, 3. Those are together. 8, 9, 6, 10 are together, and 2, 7, 5 are together. If you would have been doing store clustering, what you would ideally want to have here is the store names. The moment store names would have come, because you are knowing more about your business, and when you get the visual output which stores are together, you could have said, okay, this clustering makes sense or it does not make sense. So that's where the visual output helps. Yeah. So somehow you will have to write a code and get the store names if you are doing a store clustering in this kind of a graph. Once I have done that, I use this syntax to put my cluster names. Before I run this is my data set, though cluster numbers are not here. So what I'm going to run this one piece of line of code, and the moment I run that, cluster numbers are coming here. Yeah. And again, once the cluster is done, you have to do the profiling. Obviously, it's a small data set, so the profile output of this is very much similar to what we got in the earlier step. Okay. And once you have got the profile, what is the next step? Jargonize it, give marketing jargons. Once you have given marketing jargons, based on the profile attributes, you can now start deciding what are the various marketing campaigns that you wish to do. Yeah. So profiling. What is the next step after clustering? In this entire process, you would have noted that I give you data, customers, stores. Let's assume customers. I will take customer example rather than store, because stores don't get added on a daily basis. Let's take example of customers. You have got a certain set of customers on whom you did clustering, and then you have classified them as high net worth individuals, mass segment, privy segment, that segment, and so forth. You created some 4-5 segments. There are another 1,000 customers coming into your system. Where do you classify them? How do you classify them? Will you again run the clustering algorithm on them? Based on the clustering, you got the profile. This is the kind of a profile. Now here there is a new customer who comes in, and that customer does a spend of say 6,500 rupees, and that customer comes say 3 times. Okay, so let me put those number. So the spend of a new customer is 6,000. The spend is visits is 3 times in a month. There is no apparel purchase, and FNV items is 5. Okay, staples is 3. Where does that customer go? Why cluster 3? Because 6,000 is close to the spend 5, but that 5 FNV is also closer to it. On staples, it is between 2.6 and 4.6. So based on that, for example, let me change this number and make it 1. This is 1 only. FNV is only 1. Now where does that customer go? You will not be able to say that. Again, these numbers are all ranges. Average, when we have done average, there is range. There are some customers who are in this, would be very high on a particular dimension, very low also. All these things are ranges. We'll have to rerun. But each time you get new customer, will you keep running it? Again, don't make sense. So what is the next step after clustering? Next step after clustering is, you've got clusters. So 1, 2, 3. Can you say those are classes? Now, can I take this data set, this being my target variable and these being my independent variables? Can I run a classification tree algorithm? I can run a classification tree algorithm. Can I run a discriminant model? I can run a discriminant model. Can I run a logistic? Probably not. There are more than 2 classes, so I cannot run logistic, but I can do a probit, multinomial logistic regression I can do. Okay. Can I build a neural network? I can. So any of the supervised learning technique which can handle a target variable, dependent variable and independent variable, can we use that? I can use those techniques and build a supervised learning model. Once I've got a supervised learning model, any new record which I get, I'll pass it to the supervised learning model and then predict the class of that record. So clustering process should always be followed up with a classification model if going forward you will have to score future records. Does that make sense? So with that, clustering session, k-means and hierarchical clustering session comes to an end. A good reference material on this is basically on Google. You search something, this kind of a text, springer.com cluster analysis chapter 9. You will get a PDF. A good amount of content is nicely explained. I've gone through the document, and some of that I've taken from this document also. So it's a very good book, good PDF. Go through it. Yeah. Thank you.